Hello everyone. This is week 3 of our calculus course, and this is just a short supplementary video tutorial about the substitution technique for integration. So we're just going to go through 3 fairly short examples. As it happens, they come from exercises 5.5 in chapter 5 of Stewart's calculus textbook, which is certainly one of many good places to find plenty of examples. The link to Stewart's calculus is on the front page of our calculus website, and it's certainly a useful place to find more examples along these lines if you want to practice these techniques. So we've got 3 examples here. They're all slightly different from each other, but all of them involve the substitution technique. So we'll spend about 10 minutes maybe just running through them and having a look at how we might approach such problems. Okay, so our first example is to find the indefinite integral or general antiderivative of this expression log x squared over x. Okay, and the thing to focus on here, well, first of all, is to ask yourself, can we do this directly? Answer is certainly no in this case. There's no sort of elementary function that we know of whose derivative is log x squared over x. So then we might ask ourselves, is there some substitution that we can try? So can we rewrite the problem in terms of another variable u? So we'd like to translate the integration problem over x into an easier integration problem over our alternative variable u after rewriting everything. And the thing to be on the lookout for when you're thinking about trying out a substitution is whether your problem has some component whose derivative also appears in the problem. So what we're looking at here is the problem of integrating log x squared. So we've got a log x there, we've got a log x squared, and we've got a 1 over x dx. And we might observe that the derivative of log x is 1 over x, which certainly appears in our problem. And what that essentially means is that if we write u equal to log x, okay, we don't know in advance that we'll be able to rewrite our entire problem in terms of u, or if we can, that will improve the situation. But we can say, if we write u equal to log x, then du would be 1 over x dx. So the 1 over x dx bit will sort of get absorbed into du, leaving potentially a simpler problem. So that's a suggestion to try that. So write u equal to log x. Okay, then log x appears in our problem, and the log x squared part we can easily write in terms of u. The 1 over x is less easy to write in terms of u, but let's see what happens when we consider du dx. So du dx is 1 over x, which says that du is 1 over x dx. Okay, and that's good because 1 over x dx would translate into du when we translate our problem into a problem involving the variable u, which means that the sort of the 1 over x part here, which is causing problems, would sort of get absorbed into the du. And so rewriting in terms of u, in terms of u, 1 over x dx here, that part is du, and the other part, log x squared, is just u squared. So we can say that the integral of log x squared, 1 over x dx, this is u squared, this is du, so this is the indefinite integral of u squared du, and that is a relatively easy problem to manage. Integrating u squared over u, we get u cubed over 3, plus constant of integration, of course. And finally, because the problem was presented to us in terms of the variable x, we should give our answer in terms of x, so it'll be recognizable. U was the log of x, so this is 1/3 log x cubed plus constant. Okay, and as I've mentioned before, something that's a good habit to get into with problems of this nature is just when you've got an answer to differentiate it to make sure that you can check that your answer is correct. And certainly, and it also probably will give you a little more insight into why the substitution technique works when you see what happens when you do the differentiation, is you're essentially applying the chain rule. So if we differentiate 1/3 log x cubed, we're differentiating it cubed, so we get 1/3 times 3 log x squared multiplied by the derivative of log x, which is 1 over x. So the 1/3 cancels the 3, and we just get log x squared times 1 over x, which is exactly what we hoped to get. Okay, so there's an example. And again, the key point to be on the lookout for is some component of your problem whose derivative also appears in the problem. If you can find such an element, then making the substitution u equal to that part will have a reasonable chance of success. Okay, so that's a very typical example. And again, it works because the derivative of log x is 1 over x. If we had an x squared instead of just x here in the denominator, we would be in trouble. This would be potentially a harder problem. If we had a log x cubed in the numerator, that wouldn't be such a big problem because the substitution u equals log x would still work. So, these sometimes the substitution technique is effective, not always. And our goal really in these examples is to try to find substitutions that will be successful. Okay, second example. So here we've again got an example involving logs. And again in our problem, this time it's a definite integral. But again in our problem we have a log x. This time it appears in the denominator inside a square root sign, which is all a bit of a messy situation, but don't worry about that for now. We'll come back and worry about it later if we have to. We've got a log x and we've got a 1 over x. So again, we have an element in our problem whose derivative also appears in the problem. And that tells us that a good bet is to try substituting u equals log x. Why? Well, because the 1 over x gets absorbed into the du in that case. And the rest of our problem is at least writable in terms of u. It's 1 over the square root of log x, so it's 1 over the square root of u. So again here, the suggestion is to try writing u equals log x. Okay, then, once again, du dx is 1 over x, which tells us that we can rewrite the du as 1 over x dx. Okay, and that again is good news because this 1 over x dx is going to be rewritable as du. The remaining bit we still have to write in terms of u, but we can do it because u is just log of x. So our problem then becomes, we've got an integral from e to e to the 4 of 1 over square root of log x, 1 over x dx. This bit is 1 over square root of u. This bit is du. The limits of integration, we should bear in mind, are values of x, not values of u. So maybe when we rewrite our integral first in terms of u, we should make that explicit. We're integrating from x equals e to x equals e to the 4, 1 over square root of u du. Okay, and with the limits of integration, we have options. The easiest thing here probably is to rewrite those values of x in terms of values of u. So u equals log x. So when x is equal to e, then u is equal to the log of e, which is 1. And when x is equal to e to the 4, then u is equal to log of e to the 4, which is 4. Okay, so in terms of writing everything in terms of u now, including the limits of integration, our problem is to integrate from u equals 1 to u equals 4, 1 over the square root of u, which is u to the power minus a half, du. Okay, that's a straightforward power of u. To integrate it, increase the power by 1 from minus 1/2 to plus 1/2. Divide by the increased power, which is 1/2. So dividing by 1/2 is multiplying by 2. So we get 2 times u to the 1/2. That u equals 4 and u equals 1. When u is 4, u to the 1/2 is the square root of u. So that's 2. So this is 2 times 2 minus 2 times the square root of 1, which is minus 2 times 1. So the answer is 4 minus 2, which is 2. Okay, so again, certainly not obvious glancing at this problem that the value of that integral is 2. It's an integral of this expression, 1 over x times the square root of log x from e to the 4. So it's some kind of curve which has positive values in that domain. there you go. The answer to the area that it encloses between e and e to the 4 is 2. Okay, our third example. So here we've got another strange looking thing. E to the power 1 over x divided by x squared dx. So again, first step with something like this, just stare at it. See, is there anything that you can sort of grab onto that might give you an idea what to do with it? And certainly in terms of kind of direct methods, there's nothing that we can write down whose derivative really looks like that might spring to mind at a glance. If there is for you, great, but I think it's not something that we would be expected to immediately see what an antiderivative for that expression is. So again, then our question must be, well, what can we do with it? We've got an exponential part, e to the 1 over x. We've got a 1 over x, we've got an x squared. So is there anything in there that resembles anything else that's in there? That's a question we must ask ourselves. Okay, and you might notice by staring at it that, well, 1 over x is x to the power minus 1. Its derivative is something like 1 over x squared, something like x to the power minus 2. So a possibility is to notice that the derivative of 1 over x resembles 1 over x squared. I'll write that as a little sort of side note. So note, the derivative of 1 over x resembles 1 over x squared. That's true. Okay, when I say resembles, it's not quite that, but it's something like it. So that sort of gives us the idea, well, maybe we could try substituting u equals 1 over x. Let's try it. Let's see if it works. So try u equals 1 over x. Okay, well then du dx. This is x to the power minus 1, obviously. So du dx there is minus x to the power minus 2, which is minus 1 over x squared. Okay, well, that's good. That tells us that du is minus 1 over x squared dx, which is good because we happen to have a 1 over x squared dx in our problem that we would like to replace with a du. Okay, so that tells us that 1 over x squared dx, which is what appears in our problem, is minus du. So we do pick up a minus sign, but apart from that, we can replace the 1 over x squared dx with du. Okay, great. So we now need to rewrite our integration problem in terms of u. We've got limits of integration 1 and 2, which are values of x, not of u. Make sure that you keep that in mind and note it explicitly where necessary. E to the 1 over x is e to the u. 1 over x squared dx is minus du. So this is minus integral from x equals 1 to x equals 2, e to the u du. Okay, the values of the limits of integration are values of x, not of our variable u. But when x equals 1, we can adjust the limits. When x equals 1, u is 1 over 1, which is 1. When x equals 2, u is 1 over 2, which is 1/2. So our problem is minus integral from u equals 1 to u equals 1/2 e to the u du. Okay, so unusually in our example so far, our upper limit of integration is less than our lower one, which isn't a big deal. We just apply the same method, plug in the upper limit of integration first, subtract from that the value at the lower limit of integration. Integrate e to the u over u, we get e to the u. We've got a minus sign outside, so we've got minus e to the u. The value of that thing at 1/2 minus the value at 1. So when u is 1/2, we get minus e to the 1/2. From that, we must subtract the value of the same expression at u equals 1, which is minus e to the 1 or minus e. So putting all that together, we've got e, which is this e, minus the square root of e. Okay, so that's an answer to that one. And again, glancing at that thing, e to the 1 over x, all over x squared between x equals 1 and x equals 2, I don't think there's a quick way to really see what the area of the region enclosed by the graph of that function and the x-axis is between 1 and 2, but here it is, it's e minus the square root of e. Just a remark, maybe. It does happen quite frequently with integration problems that there's more than one substitution that would work. So here you might also notice, and maybe some people did already, while looking at this example, that we could also write u equal to e to the power 1 over x. That would also be an effective substitution. We could also try writing u equals to e to the power 1 over x. Okay. Then applying the chain rule to that will give us du dx. Okay, this is an exponential, so if differentiated as an exponential, you get e to the 1 over x. And then applying the chain rule, we must multiply that by the derivative of 1 over x, which is minus 1 over x squared. So this is minus e to the 1 over x squared. So what we can observe from that, using the usual substitution machinery, is that du is equal to minus e to the 1 over x squared dx, which is pretty much exactly what appears in our original problem, except without the negative sign. So this is saying e to the 1 over x squared dx is equal to minus du, and our problem just amounts to minus integral of du. And again, after substituting our values of, after replacing our values of x with values of u, we get 1 for the lower limit, 1/2 for the upper limit. Actually, excuse me, that is not quite right, what I just said. Our problem is integrate minus du from x equals 1 to x equals 2. So integrate du, you get u, so this is minus u from x equals 1 to x equals 2. U is e to the 1 over x, so when x equals 1, u is e to the 1 over 1, which is e. When x equals 2, u is e to the 1 over 2, which is the square root of e. So finally, we have minus u evaluated below at e and above at the square root of e. So we get minus the square root of e minus e, which is indeed, again, e minus the square root of e. So it does happen quite often in these substitution problems that there's more than one candidate for a substitution that'll work. Okay, so thanks everybody for coming along. If there are more examples that would be useful, or if you'd like a few more, just let me know. We can certainly add a few more. Okay, thanks everybody. See you later this week.